Can you hear me? Hello? Can you hear me?
Yes, sir. Yes.
Okay, I'm sorry I've been late. पता नहीं मेरा laptop though it's new and then it takes time to start on that. Sometimes. Okay, so that today I want to start this pointwise uniform conversion. This is very important, but basically you see I am not going to teach much of this. Okay, I am just want to give definition of pointwise and uniform convergence, and then I want to give a couple of important theorem. But you should read the other note, that note 21, I think. Okay, so what is pointwise convergence and uniform convergence? Okay, first come here. These two are also important in major theory also. Pointwise convergence. Now look, first I am not working with the functions and that. First, let me, when you did two sequences, take real sequences. Okay, xn goes to x and yn goes to y. So you will get this thing, that given epsilon the greater than 0, you will get 1 here, n1, such that you have this for all n greater than equal to n1. And here you will get, for same epsilon, there exists n2 belongs to n such that yn minus y less than epsilon for all n greater than equal to n2. Now if you take n not equal to max of that, then you can see both, you can write this thing. Okay, right. But if you have infinitely many such sequences, suppose this infinitely, look, that means one n naught is working. But if you have infinitely many sequences, then this may not work, because then you will supremum of all these things. For all each sequence, you will take supremum of the sum, suppose nk, and that may be infinity. That may not be a natural number. So this kind of trick only works for finitely many sequences. So this infinitely in, this is making problem. So pointwise convergence, and difference between pointwise convergence and uniform convergence is similar. Okay, so actually the later on we'll see every sequence is a function also. Okay, so that now come here. We have used already pointwise convergence. Suppose you have a sequence of functions. You can take for the timing from R to R for understanding the concept. Okay. Suppose at a point x belongs to R, I don't know. Fnx converges. Suppose converges some y. Okay, suppose. Look here. So you are having a sequence of functions, and out of that, if you fix x, you are getting a sequence of real numbers. This is actually a sequence of real numbers. We have done this similar thing when we proved bxd is a complete metric space. There, if you look, we were defining through pointwise convergence. So let me tell you that. So you are getting sequence of functions, and at each point you are getting a sequence of real numbers. And since this y will depend on this, suppose for each x belongs to R, Fnx converges. Now look, I can get a new function. This I did. y equal to, since this will depend on the x, this sequence, write y equal to define. Y equal to fx, define. So define f equal to by this. Look, this makes sense because I have assumed this converges. And since the sequence will depend on x, that is on this point on x, that is the called point. So given a sequence of functions, you are getting a sequence of real numbers. Now suppose it converges, then I can define a new function that y equal to fx. That means in this case, I can write fnx goes to fx for each x. Could write all, but each x is better than this. This called pointwise conversion, because now you see this is called pointwise convergence. There can be other types of convergence for the functions. Pointwise convergence. That means when you're talking about pointwise conversion, make sure that you are talking about a sequence of functions, and each point you are plugging in. That you are getting this here. Okay, fnx. This is a pointwise convergence. Now look here, if you have pointwise convergence, if you change x, that means what you will be getting. Now look, fnx tending to fx, that means like this example I was giving for sequencing. Now look, here you are getting x equal to r, particularly if you take x is a set, you can take domain, and x is infinite. Then you'll get infinitely many such sequences, but for each x, you're likely to get a different sequence. Okay, so fnx will be different, so you get infinitely many such sequences. That means similar to that problem, here given epsilon greater than 0, there exists n naught, so such that fnx minus fx less than epsilon for all n greater than equal to n naught. Now you see, usually it is, now I am just concentrated on this sequence. So this epsilon, obviously this n naught depends on epsilon, that is a function of epsilon. Also look, if I change x, I will get a different sequence that I was explaining before. So that this n naught not only will depend epsilon, it will depend on the sequence itself. That means the sequence is changing with x. That means n naught will be a function of both epsilon and x. N naught not only for a single sequence, it is n naught is a function of epsilon. But when you are having different sequences, look, if I change x, I will get another sequence. So that means I'll have to keep track. That means n naught not only will depend on epsilon, it will depend on this sequence also. That means it will depend on x, because sequence changes with as x changes. So that you get n naught, which is a function of both epsilon and x. That I was taking infinite collection. Here, when x is infinite, you are getting infinitely many sequences. That's the problem. If you get finitely many sequences, it's not a problem. You just take the max of like all these n zeros and that. If you have finitely many x, but infinitely many if you have, then you don't have that max on to work. You'll have to take supremum, but supremum may be infinity, may not be a natural number. So that these you get. That means for each x, you are getting a sequence. This called precisely pointwise convergence of f. Okay, it will depend on x. Okay, right. So that I have given the given epsilon greater than 0, there exists n naught. That first definition 6.2. N naught depends on both epsilon and x. That is n naught bracket epsilon x. That means it indicates that is a function of both epsilon and x. Okay. Now suppose I have a situation that I get, suppose, it's not I always get, that n not only depends on epsilon. Okay. If you have this, suppose if you have this, then it will mean what? That means given epsilon greater than 0, there exists n not for all n greater than, and it won't depend on x, and for all x belongs to x. Suppose this n naught doesn't depend on x. That means this n naught only depends on epsilon, so that it doesn't depend on x. That means it works for all x. Suppose it is possible. This, then it is called uniform convergence. Uniform convergence is much, look, obviously if it is uniformly convergent, it is we call uniformly convergent. Then it is pointwise convergent. But there are examples, many examples, pointwise convergence may not imply uniform convergence. It may not. This is true always by definition. But this is, in fact, the type note, you will see that is very important. I think in the beginning of the 19th century, I think probably 1826. In fact, Cauchy, who was one of the founders of analysis, he made a mistake in that. What is the importance I am telling you? Look, if I have sequence of continuous functions, even from R to R, suppose I have all these functions are continuous. Okay, all these functions. Then suppose you have pointwise limit only. But this function may not be continuous. That is the difference. But if it is uniformly convergent, then it will be continuous. So that's the first difference. That means if you have uniform convergence, then this function will also behave as good as this sequence of functions. But if it is only pointwise convergence, then it may have the sequence of continuous functions, but this is not continuous. For uniform convergence, it is uniform word is there, that because of the uniformly for all x. Same uniformly for all x, same epsilon is working, like uniform continuity. That is the word uniform. Why I'm telling you that? That means pointwise convergent limit of a sequence of continuous function may not be continuous. The uniformly convergent limit of a sequence of continuous functions will be continuous. Exactly at this point, Cauchy made a mistake, because Cauchy was not aware of the idea of uniform convergence. So he gave wrong result. It is Abel who actually was more interested in group theory and algebra. He pointed out, he gave the correct proof actually, but he didn't work on this further. Okay, so he said it is something stronger convergence is required. So he introduced this idea, uniform convergence. Okay, and unless uniform convergence is there, the limit function may not be continuous. The example is here. Looks simple. Here x you take 0, 1. Okay, and for each n, you define function, real valued function, simple function you are defining 0, 1 to r by fn x equal to x to the power n. That means if you are picking up n, keeping it fixed, then this is n fixed, x to the power n. Obviously, each of them is a continuous function. Look. Now look, pointwise, what is happening? If I take fx equal to 0, if, look here, this note here, this is strictly less than 1. Then look, fn x goes to fx, pointwise, what you are writing. When uniform convergence, you write functions like this, but pointwise convergence for all x belongs to 0, 1. Okay, because it actually is, since it is less than 1 and it goes to 0. Okay, and for 1 everything will be 1. It will be constant sequence. That means pointwise it is converging. Okay, right. But this convergence is not uniform. Reason is, you can draw the picture. You will see that what will be the problem. Suppose, so this is 1. Okay, so for n equal to 1, this is straight line. For n equal to 2, this is parabola. So it will go like this. Now look here, the problem. Problem is problem point 1. First of all, also see that f is not continuous at 1. So f is not continuous. When f is continuous, the whole set means f should be continuous at each point. So f is not continuous on 0, 1. Okay. Look, we have apparently nice functions. So sequences are also nice, and it is converging to this limit function, and that is not continuous. Okay, right? And you see that what is the problem? Problem is this 1. Okay, why 1 is problem here? Okay, let me tell you that. If you go for uniform convergence, you see the 1 is giving the trouble. Okay, actually, uniform convergence means what? Let me explain. Actually, I have drawn a geometric figure in the last page, page 185. Okay, else on page, let me tell you that. Look, if we have uniform convergence, suppose Fn, actually we have two notations. In measure theory particularly, pointwise, this is pointwise we write, and Fn uniformly. Sometimes we just write P notation for pointwise and uniformly. Now look, if this you have, then I'm taking time to explain. That is very required to understand the difference in the concepts. You should understand, because you misunderstood. Okay. So it is not unusual that at the first instance you will also misunderstand. You won't have proper understanding. So you need proper understanding. Look here, if you have this, that means given epsilon greater than 0, there exists n naught or n epsilon, you write. Okay, belongs to n. Here n epsilon means it is only depends on epsilon, such that fnx minus fx less than epsilon for all n greater than equal to n epsilon, and for all x belongs to x. Okay, each of them is a function to this. Look, I do not need any metric and topology right now. Only when if we consider continuity and that, then I need. But right now I am just giving the definition. I don't need any topology on x or topology on y and then. Okay, R, this thing. For definition of this pointwise uniform convergence. Now look here. It means what? It means we are getting fnx less than fx plus epsilon, fx minus epsilon for all x belongs to x. Okay, that means if you take given epsilon, you take two functions. You call it, you can call it f epsilon, but call it h epsilon, right? And it call it g epsilon. This function. That means h epsilon x is fx minus epsilon. You have picked up epsilon, now you are keeping it fixed. And g epsilon x is fx plus epsilon. So if you draw the graphs like this, this is your x-axis, and this is your r. That's always sometimes presented geometrically. Now look, That means epsilon is a constant function. This means epsilon x doesn't depend on x. So basically constant function. So that means you are getting a function f minus epsilon. Here you are getting f plus epsilon. Because if you take f plus epsilon by the definition of addition of two functions, fx plus epsilon x, but epsilon is a constant function. So this is fx plus epsilon. Similarly for that. So that suppose graph you are taking, suppose this is your graph. Okay, up to this you can take. This is your f, suppose. So that if you take a plus epsilon, f minus epsilon. That I have drawn in the last page. So this is your f minus epsilon. And this is f plus epsilon. Okay. Now look here, what I am getting actually. I am getting, look at the graph. It is for all x. That means graph of f is lying in between. Look, that means I am getting this. Not for all n necessarily, but for all n greater than equal to n epsilon. That means graph of fn that means has to be lying in between these two like this. It can't go outside this. That is the thing for all n greater than equal to n epsilon. Got it? If one of them, if you don't never get any epsilon, whichever n you choose, not epsilon, given epsilon, whatever n you choose, you see at least one of them is going out. Okay, that means it is not uniform convergence. So uniform convergence geometrically, the idea is that graph after a while, they're all lying inside this. That is the picture I have given in page 185. Now look, what will happen for x to the power n, that fn x, if you take x to the power n. Now look here. Look, fx is coming what? Look, after this it is coming 0. And after that is coming 1. So if you take f minus epsilon, f plus epsilon, then it will look like what? That means less than 1, it will look like this, and 1, f1, fn1 equal to always coming 1. So 1 plus epsilon, this is 1. So this will be like this. Now look, but the graph you are drawing, look, is this, look, around the point 1, it is going out. You will never get that whatever you choose, it is never lying inside the entire thing strict. Okay, you call it epsilon band of that. Okay, because 1, you look, it is going there, reaching there this way. This is, but your f plus epsilon, f minus epsilon band of f is like this up to this, but 1 is here. 1 is not, 1 is making problem. So this is, that means what I am getting, that means fn to take fn converges pointwise. Look, limit if it converges pointwise and that convergence, that by the uniqueness of the convergence of the limit, okay, sequence of limit of the convergent sequences, it has to be unique, so that it's not if it converges pointwise to a function, it will converge to a uniformly to another function. That is not possible. Okay, f where fx equal to 0 when you have this and 1, it's equal to 1. Okay, and fn does not converge uniformly on this. Here, let me to page 178. Apparently, I have written a wrong statement here. This that I wrote that I think from the below you look at 1, 2, 3, 4, 5, 6, 7th line. 7th line from below. Usually in the journals, when you check the galley proof, they write line -7. That means from the below. 1, 2, 3, 4, 5, 6, 7. I said, check that Fn, I asked uniformly, since one is making problem, if you apparently student may think that if I gave this out, okay, this statement is wrong. Okay, I was not very careful, alert on that. Okay, reason is if you go to the net, you will see that they always say that if is this, when it will be uniformly convergent. Actually, they say, sorry, on this where k is this, strictly less than 1, this interval, close interval. Okay, that means it has to be away from 1. That means actually the native look, they do not actually address the problem. What I can tell you, somebody got the highest marks on that in minor. I think I'm giving an exercise, you can try it. That what I'm saying, you think about. I didn't prove it, but later on I thought about it, that Fn, that function, suppose let a subset of non-empty subset, of course. Look, I can define an A need not be an interval. Show that Fn converges uniformly, f is that function, uniformly to 0. Actually 0, you can say uniformly to the constant function 0 or you can take this thing 0, constant function 0. If and only if 1 is not closure point of this, is not a closure point, there is also thing accumulation point, because it is subset of the real line, it is 2 on space. 1 is not a closure point of E. Their problem is that this 1 is a closure point of this set. So that's why the statement is wrong. So you should be able to prove it. If you can prove it, send me the proof. Okay, right. So that Fn converges uniformly to the constant function, uniformly on A. On A. Okay. I can take a subset. Look, if it converges uniformly on the bigger set, it will converge uniformly on the smaller set, but not the other way through. Okay. So that here I am saying that A will converge as long as 1 is not an accumulation point, a closure point of E. Okay. So that's why the big thing. Okay, so that you should understand the difference between uniform convergence and these I have explained 174, 79, sorry, that graphical representation. And then this is the example everybody uses to explain the difference between pointwise convergence and uniform convergence. Okay, so you should look at my other note that was taken from my book that I also mentioned. I have written with two persons. One is my supervisor, other one who did PhD under my supervision. Okay, so that and this is very important even for in applied mathematics also. Okay, right. Now the thing is, you should read this page 180. I have talked about stone-wise trust theorem. That I will tell you that why stone-wise actually two theorems are important here: Ascoli-Argela theorem and stone-wise approximation theorem. The proof given in the book by Alibrantis Berkinshaw, they have proved a series of lemma and then they prove the main result. But proof of one lemma is incorrect actually. That I explained in that. But it can be corrected. In our monograph, we have given a corrected proof on that. We have given a correct proof on that. I think they were not allowed. That's where they are making mistakes on that. If you are interested, you can read the proof. You can read the theorem. Okay, and actually, best thing you can prove with this Royden, Royden's real analysis. HL Royden. Actually, usually more third edition is available in India, but now fourth edition is also available. Fourth edition is a very revised edition, and that I think Royden is not alive anymore. So, person who did, I think Fitzpatrick, he revised that book to the fourth edition. Okay, this is available in India. Indian edition is available. In this book, you can find the proof of that also. Our proof is a bit different because we use straight definition of compact sets instead of sequential characterization. Okay, I will come to that point. Okay, so that here you look theorem 6.1 that I was telling you that theorem 6.1. What is theorem 6.2? Look, we have already given an example that pointwise convergent. Look, we already have given the limit. The pointwise convergent limit of a sequence of continuous functions need not be continuous. This historically, I already told, historically even Cauchy made a mistake on this. Okay, pointwise convergent, but sequence of continuous. But if I take uniformly convergent, if I cross it, the uniformly convergent limit of a continuous function is continuous. Okay, this is the first big difference between uniform convergence and pointwise convergence. And pointwise convergence limit need not be continuous function. That was the example I was discussing. So that is exactly theorem 6.1. That means since I am talking about continuous functions, of course, real valued functions, because otherwise you on that side you could generalize. If you could take a metric space, you could generalize that. But right now we're talking about pointwise convergence, uniform convergence of real valued functions, sequence of real valued continuous function. Okay. But when you talk about continuous on the real line, I know this. I have this thing. That's the usually you take. But on the domain X, you need a topology. Otherwise, you can't talk about continuous functions. That means, suppose you have this Fn X tau, the topological space. On this side, you have R. That means you have this topology. Suppose each of them is continuous. Okay, and for all n. And also suppose you have a function here, x tau to this, but that I do not know, that I need to prove. Suppose this is a hypothesis. Suppose Fn tends to F uniformly on X. Okay, these are all hypotheses. This is the short version. I am explaining this. What is this means? That means here we are having a sequence of functions converging uniformly to F, and those sequence of functions continuous. If you have continuity talking, then obviously you need topology on both sides. So you have a topological space, you have this on the real line, you have the usual metric. Then conclusion. F is also continuous. Got it? This is the thing. Okay. I have given the proof. Proof is not difficult at all. But let me tell you about some technique here. Technique, if you look, then I have used triangle inequality, and I have given epsilon. I have three parts, epsilon by 3. So by using triangle inequality, I have got this epsilon by 3 plus epsilon by 3 plus epsilon by 3. So equal to epsilon. So if instead of taking, if you don't take epsilon by 3, you'll get epsilon plus epsilon plus epsilon, you'll get 3 epsilon. Still it is fine, because epsilon is arbitrary. So that there is no difference between 3 epsilon and epsilon, because I am choosing for any arbitrary epsilon. Why I am saying this argument, it is a standard argument in analysis, and this is called 3 epsilon argument. Name of the argument is called the 3 epsilon argument. 3 epsilon argument means you basically, for your argument, you make three pieces. But the funny thing I am telling you, usually it comes in 3 parts. Often you will get that. In other parts also, in some other theorems, you get 3 parts. But sometimes, occasionally it happens, you have 4 parts. That is 4 epsilon or 5 parts. Okay, but still, we do not say that 4 epsilon argument, 5 epsilon argument. Again, you call here 3 epsilon argument. 3 epsilon argument means you'll have to split into pieces. Okay, usually that come into 3 pieces, but sometimes it may be 4 pieces, 5 pieces, or even maybe 2 pieces. But still we call it 3 epsilon argument. 2 pieces you have already got uniform continuity. When I say last time, look at the argument that if your domain is compact, then any continuous function is uniformly continuous. Actually, you're splitting into 2 parts. That's why you are taking epsilon by 2, epsilon by 2. Instead, I tried to explain to you that why you are taking 2 epsilon, so that you'll end up with epsilon. Okay, basically 2 pieces. Here we have 3 pieces. Okay, once you understand that technique, okay, so that it will be simple. Now look, in this argument, one thing is, when you say that, look, uniform convergence, suppose uniform convergence. So given epsilon greater than 0, there exists n epsilon, only depends on epsilon, such that fn x minus fx less than epsilon for all n greater than equal to n epsilon, and for all x belongs to x. Here n epsilon I have taken k in that, okay, particular one that, but not that. It's, listen now, particularly all n greater than equal to n epsilon, particularly say it will be true for this. I could take any n greater than epsilon, I could keep it fixed. But I'm saying I will get this for all x belongs to x. This thing. Okay, right? That exactly I have used. Okay, now let me give you the proof of this. You may wonder I have not written this definition of the sequence and the convergence of. I am just taking one this. I am just telling you that what I need. So that we need to show the limit function. Now the proof. I need to show f is continuous on x. But on x means what? F is continuous at each point of x. So that means if you take any point x arbitrarily chosen, I need to show that f is continuous at a. A was arbitrarily chosen. Okay. But then what does it mean? Fx to r. Look. Here for the real valued function, you have simpler description of the continuity. Look. Here the continuity given epsilon, I'm saying this what this will be enough because you choose this is a ball here. Look, any neighborhood of FA will contain a ball around FA. So the ball around FA is actually will be up like this. This. And I need a neighborhood of this. A neighborhood of this, that an open set containing U such that FU is contained in this. I am using the definition of continuity at a point. And for this side, I have choosing apparently basic neighborhood ball, but that I can choose because any neighborhood of FA, that means any open set containing FA will contain this and this. And if this happens, that will also be true for every neighborhood of FA. So that basically I need to choose, I need to show this that existence. We need to show that there exists a neighborhood U of A in X tau such that Fu is contained in this. That is Fx minus Fa less than epsilon for all x belongs to U. Okay, that. Now you see that what I have done. First I said Fn converges uniformly to F on X. So there exists K belongs to N. That K you can choose an epsilon such that for all X belongs to X. Epsilon by 3. I am taking epsilon by 3 because I will get 3 part. So eventually you will be happy, you will get epsilon. But if you started with epsilon, you will get 3 epsilon. For all x belongs to x. Here I am using uniform convergence, but I am keeping one integer fixed. Okay, because I will use the continuity of fk. Since fk is continuous on x, fk is continuous at a. Hence there exists a neighborhood of a u such that I will have this double star, the condition. I am using the continuity of fk at a. Now you see fx minus fa, that mod, I have done this 3 parts. Now look, the first part fx minus fk x, that is less than epsilon by 3 by star condition, and fk, this is true for all x, so particularly true for a, so that mod fk minus fa less than epsilon by 3. Okay, right? And by double star, look, I am using the for 2 parts I have used uniform convergence. First part and the third part. At the middle part, I am using the continuity of fk at a by this double star that I said that you got this thing. For 2 parts I am using uniform convergence and 1 part I am using the continuity of fk at a. So you are getting just 3 options. That is the argument, nothing else. Okay. In fact, could look at last year's major problem. In fact, I have given a question and I have given hints. It can, I think, last question. I think it is last question. This question number 7. Hmm? Question number 7. Okay, you can last year's major exam, you can see that. Okay, right? Hmm? And there I said, can you use the technique of the proof of theorem 6.1? This is theorem 6.1 in the page 180, 81 of my class. So that basically you need technique. Though the question apparently is different, I have talked about equicontinuous. That I will say that. What is equicontinuous means? Hmm? Okay. So this is the proof. Okay. I will just come back after 5 minutes of that. I will teach you that. Let me see that. I hope I will be able to teach you 2-3 pages. Hello, are you ready? Hello? तो भाग गया क्या?
Yes, sir.
Okay, let me tell you that now. Okay, lest I forget, and let me tell you that I think it won't make problem in that. Instead of Friday, I will take class on Friday. I will take class. I will take class on Saturday. That is October 30. This time I will start. It may maybe 5-10 minutes late. Okay, but October 30. Right now, though I have two more one more theorem at least, two theorems, but actually I just I won't prove anything. I just want to talk about this. Now look, remember that if you have a set x just, then r to the power x is a collection of all real valued functions. That means this. And for pointwise addition and scalar multiplication, this is a vector space, linear space. Over R. Okay, right? Under the usual addition of functions and the usual scalar multiplication. Usual addition is pointwise addition and pointwise scalar multiplication. Okay, and Bx is what? This function here, that means Bx bounded functions. That means f belongs to Rx such that f is bounded. That means look, f is bounded means fx is a bounded subset of R is bounded in R. And already since you have seen that is a vector space, so that means Bx is a subspace. Bx is a linear subspace of this. Look here, linear algebra and topology, they are coming. Because particularly I have seen that Bxt is a complete metric space. That I proved. Now you look here. Remember that D, that is uniform convergence, we have dealt with before, but we have not specifically used the term on that. But now look, D here between two functions, this metric was, we called it supremum metric, sup of fx minus gx. So since it is defined through sup, it is called supremum metric. Look, in order to define the metric, I need bounded functions. Okay. Now you can see that, go back to that. If we sequence a convergence to this with respect to this metric, T in Bxt. Look here, is supremum I'm taking. So that means the graph between fx minus gx, that has to be, to take less than epsilon. That means the entire graph will have to be the difference between their graph. That means if you take f minus epsilon, f plus epsilon, the graph of g will have to be in between these two functions. Okay. Now we can check that it is easily followed from the definition that you, if and only if Fn converges to F uniformly. Okay, so this just follows from the definition. Sup I am taking, and if there is less than epsilon, that means for all x automatically. Uniform convergence means at the same time it comes for all x. So when you make it less than epsilon, that means for all x, this difference will be less than epsilon. Okay, so that this is the median. So that this convergence is uniform convergence. That's why supremum metric is also called uniform metric. Name. Okay, right? Got it? Now, here I don't need any topology. Now, suppose you have a topology. Okay, suppose X tau is a topological space. Then I can talk about Cx. Cx is this, that f belongs to R to the power x, but that means f is a function from x to R and f is continuous. Okay, f is continuous. Now look, again you can prove that sum of two continuous functions is a continuous function, and scalar multiplication of a continuous function is continuous function. That means Cx is a vector subspace of R to the power x. But intersection of two subspaces again a subspace. So that Cx intersection Bx is also vector subspace of R to the power x. Okay, now what does it mean? This means it is continuous. Here I am having a topological space as well as bounded. That means this is this f x to R, this for this, such that f is continuous and bounded. Usually we use this notation CBX. This notation. Yes, C for continuity and B for bounded, CBX. So this is CBX. Now look, so this is a subspace. But not only that, since on BX I have, so it's just intersection. So particularly CBX is a vector subspace of Px. Okay. Now on Vx I have this metric D. That means I can consider this metric also. Because as a subset of this, it will inherit this metric D. Now I want to, that I claimed the next theorem and that, theorem 6.2, but proof is immediate. I am just, this is also complete metric space. This is a complete metric space. But यहाँ पे बहुत ज़्यादा झंझट नहीं है completeness, because we can use the fact, okay, in order to prove is a complete metric space, we need two facts. Facts one, Pxt is a complete metric space and you need previous theorem, theorem 6.1. That means uniformly convergent limit of a sequence of continuous function is continuous. If you have this and each of them is continuous, then f is continuous. Uniformly convergent limit of a sequence of continuous functions is continuous. This you need. Look, then proof is immediate. Now look, all I need to show closed subset of a complete metric space is complete. That we have done. This is a very simple thing. Just use the definition. Closed subset of a complete metric space is complete. So I need to show CPX is closed in this metric space, closed in BX. Okay. That means what? You take F belongs to CPX bar, closure in BX. Okay. It is all metric space I am considering. So by the result on the closure point, there exists a sequence Fn in CBX such that Fn goes to F in this metric, because that is the metric space BXT. My whole metric space is this. Okay, got it? Now you see that I'm getting, because BXD is a complete metric. First of all, I am getting this. There exists sequence such that this is going. Now already I told you this metric D, F is in F. Right now I know F in BX. I do not know in the closure of this. I do not know whether F is in CBX. F in CBX, look, F is already in BX. Only I need to prove, I need to show that F is continuous. But that is immediate. Look, here I told you this convergence with respect to the metric T is nothing but uniform convergence. Uniform convergence. Okay. And so this is the limit, uniformly convergent limit of a sequence of continuous functions. Look, Fn, they are coming from CPX. So each Fn is continuous. So that by the result, theorem 6.1, by theorem 6.1, F is continuous. Okay? That I got, F is continuous, but of course, all I need to show that F is continuous, F is bounded. So that F belongs to everything I am working inside Px. Okay, so that F belongs to CBX. That means CBX is complete. CBX T is a complete metric space. This is a proof. I am just using the fact. What does it mean? This is convergence with respect to this metric D is nothing but uniform convergence. And I am using theorem 6.1, which says that uniformly convergent limit of a sequence of continuous functions is continuous. Okay, and corollary 6.3, immediately look. Last week I taught you that if you have continuous function and at the same time this tau actually is compact, is a compact topological space, then Fx, continuous image of a compact set is compact, Fx is compact in R. I did last week. But in a metric space, every compact subset is closed and bounded. So particularly Fx is bounded. That means if your domain is compact, if x tau is compact, then every continuous function is bounded. If x tau is compact, then you are getting first thing, CBX is same as Cx. But already I have proved CBX with D is complete metric space. So that in this case CXD will be a complete metric space if X is compact. Now let's comment that. So this I got. Okay, now remark 1, 2 is coming on that. Okay, that theorem 6.4 or later on and prove. Now come here, the CXT. Suppose X is a, if you feel comfortable, you can take X is compact. X is a compact metric space. Because this has big application in many areas like PDE. You will be doing a course in PDE, I think next semester. No, third semester you will be doing it, which I guess so, third semester. compact metric space, suppose. Then Cx will be same as Cpx, so that this you have got a complete metric space. Here I have not talked about equicontinuity. I will talk about equicontinuity in the next class on that. Okay, that is the thing. That I have given a problem the last year, last problem, question number 7. Now look why I need to talk about equicontinuity. So given a metric space, two problems are always there. First, whether it is a complete metric space, and secondly, what will be the compact subset. Though we have nice characterization of compact subset in metric space, still, like Heinz-Borel theorem, why it is important? It gives you it gives a complete characterization of compact subsets of Rn. That means if and only if it is closed and bounded, which is required. If you have a compact subset in metric space, it has to be closed and bounded. And Heinz-Borel theorem is saying converse is also true. Similarly here, look, CXT, it's a compact metric that already I know complete metric. The first question is answered. Now, what will be the compact subsets of this? The compact sets in this metric space. Because this is all dealing with functions. In other areas like PD, whenever you deal with function, nice from real valued functions on that. You'll have to basically deal with this. Minimum thing is start with continuous function. Then you see whether differentiable, even in the R, if you take x. Okay, first you need the continuous function. Now here it is very important that what will be the compact sets in CXT. That means, is it possible that we have analog of Heinz-Borel theorem here? Heinz-Borel theorem here. Exactly not the version analog of Heinz-Borel theorem. Okay, here you have a theorem. Okay, analog, and that is famous Ascoli-Argela theorem. You can go to the net to see that. There are two Italians. Look at the history. One of them did special case, one of them did the general thing. Who is which one? You can see that Ascoli and Argela. Anything ending with I or A usually is a Latin, is an Italian last name. But sometimes in French or Spanish, you may see that last name ending with I or A. But I'm telling you, they are originally actually Italian, because in France and Spain, there are many Italian immigrants. They are living there for hundreds of years. Okay, so usually with I and A ending with this. Ending with I and A, usually Italians. So here that the Ascoli-Argela theorem that I was talking about, Ascoli-Argela theorem is analog of Heinz-Borel theorem. First of all, that means suppose X is a compact metric space. I won't give you the proof on that. I am just explaining. That's the note I put, that the type note. You can see the proof. X is a compact metric space, but you need this result. And you are considering this metric space. It's a complete metric space. Okay. Now suppose A is a non-empty subset of Cx. Now the question is that, like Heinz-Borel theorem, the equivalent criteria, the following are equivalent, that I'm just telling you that I won't do it today, but I will do in certain. A is compact in CXT Look, here Cx is same as Cbx because I am taking this. Okay. B, look, A is compact. Any matrix space it has to be closed and bounded. So A is closed, bounded, but only closed and bounded won't give you the compactness. The converse thing that B implies in that you can easily do that. Closed and bounded. That means you need plus something. This is the big question. Plus something. Look, A is compact. A is a subset of Cx. That means A is a collection of functions. A is a collection of functions. Now A is closed, bounded, plus something you need. Plus something. This something means equicontinuous. Equicontinuous. Equicontinuous, look, equi. It is continuous here, that you understand. Equi. Okay. So A has to be equicontinuous. And then these two are equivalent. So it is high-numeral analog for this metric space. This is known as Ascoli-Arjela theorem. And this is a very strong tool for other areas of mathematics like PDE. PDE is a core course for you. Okay, right? The Ascoli-Arjela theorem. And also, if you are later on, if you become interested in function analysis or operator theory, then Ascoli-Arjela theorem also will be important for you to know. Okay, so now I'm just explaining. I will again define equicontinuous. I am not doing theorem 6.3. That is Dini's 6.4. Okay, so that is definite. Theorem 6.4. That I will do later on. But I just want to explain what is equicontinuous. Don't worry. Saturday again I will define equicontinuous. Equicontinuous. Now look, that means we are having a set Cx. Look, it is not uniformly continuous, a non-empty set. I am saying it is equicontinuous, the term. When you do mathematics, first you need to understand the definitions well. Only then you will be able to understand the results and then the proof. Okay, so that equi. Okay, like uniformly continuous, you had uniformly chosen, given epsilon, you could choose delta uniformly. Now look, since equicontinuous, first you define continuous at a point, similarly equicontinuous at a point. So at a point, A belongs to X. Look, it's a real valued function. Remember that real valued function, when you have that, if you have this, that's the criteria I have already used. Simple criteria. A belongs to S, then F is continuous at A. If and only if given epsilon greater than 0, there exists a neighborhood Q of A such that Fu is contained in this interval. That means any x here, fx is goes here. That means that is fx mod fx minus fa less than epsilon for all x belongs to Q. See, on that side we have the metric space R, and that we can use this thing. Given the usual, the very beginning basic delta epsilon definition between two metric spaces, that I can use it. Only thing here you will have a neighborhood. Okay, right? So that now look, what is equi? Here you have a collection of functions. Collection of functions. Suppose continuity, and I'm taking this is fixed. What will I mean equicontinuous? Now look, if I change f for same epsilon, very likely I will have a different neighborhood of a. Different neighborhood of a. Now if you have two functions, you say two functions, look, here I get a neighborhood u1, that means open set containing A. Here we get an open set containing open set u2 containing A. Then I could take this. That will be another open set containing A, and that will all work because Fu1 is this, Fu2 will satisfy this, so Fu will satisfy. That means if you have finitely many, I could take the section. And that means what I'm saying? That means same neighborhood will work. If I have finitely many such functions, continuous functions, then I could have a single neighborhood here. But what about that if it is infinite? I may not have it. That means exactly that is the equicontinuity definitions. Suppose for each f belongs to a single neighborhood works. Single neighborhood. Then we say that f is equicontinuous. A is equicontinuous at A. Okay, A is equicontinuous. If single neighborhood works for all f belongs to A, then we say that f is equicontinuous at A. So let me write it that what actually I'm saying. That let f x tau, sorry, wait a minute. Let x tau, I can do it for general definition. X tau be a topological space. And non-empty subset Cx. Right now for equicontinuity, I don't need any metric on that. Okay. So let A belongs to X. We say that in that type note you'll find that we say that A is a collection of functions. A is equicontinuous. This adjective, equicontinuous at A if given epsilon greater than 0, there exists a neighborhood U of A in X star such that this thing, if you contained in this, be careful, there is a neighborhood U of what is F? For all F belongs to A. That is Fx minus Fa less than epsilon for all x belongs to U and for all f belongs to A. That means single neighborhood is working for all f. Okay, that's why it comes equicontinuous. Okay, you can look at the meaning of the word. It is originally, I think, Latin word. Okay, but French, Italian language they are used commonly. Qui. Okay, that is qui actually in some sense uniformly. That means same U is working uniformly. U is basically uniformly U is working for all F in A. Uniformly U is working for all. Already uniformly is there, so it is came in that equi. So this is the definition of equicontinuous. And Ascoli-Arjula theorem I told you that if it is closed, bounded plus equicontinuous, then it will be compact. Otherwise, that particularly any compact subset, if you take compact subset, it has to be equicontinuous. So I will continue this thing. Okay. Actually, I will prove Dini's theorem, and not much I will teach, and I will again explain that this equicontinuity. I won't give you the proof of Ascoli-Arjula theorem. If you are interested, you can prove that. That is given there in that note, Ascoli-Arjula theorem. But I will explain Stone-Weierstrass theorem again. The Stone-Weierstrass approximation theorem, that also you need to know. At least the statement you need to know. Okay. So see you on Saturday, 30th October. Fine? Okay, bye.
Thank you, sir.
You're welcome.